Hello everyone, welcome back to my channel. This is an introductory video on the lecture series of signals and systems. Signals and systems is one of the basic concepts in all of engineering, and it's especially important for electrical engineers. So let's see what's in for today. So first I'll tell you some tips to learn this topic at its best, and then I'll suggest you some recommended books, and then we'll come to the topic of what is a signal and what is a system. And just before concluding, we'll also see why do we need to define a size of a signal, or what is the size of a signal. So let's get started. Firstly, coming to the tips. So do we ever feel lack of focus while watching videos? Right? We all feel the same, right? So one important suggestion I would give is to take notes. So note taking will help you improve your attention and focus. And by note taking, I don't mean full-fledged notes to be taken. I just mean that like you can keep a note nearby you, and whichever you feel important, you can note it down. And also you're welcome to take full-fledged notes as well, because it will be helpful for you to revise later. Secondly, what should be your optimal study plan, right? So for this topic especially, so the lectures will comprise of 30%, which is, you may be watching this lecture, so it will constitute of 30% of your learning, and 30% will come from reading books, and 40% is devoted to practice, because it is a math intense course, right? So you need to practice well. So in my college days, when we were learning this topic, right, we used to have a daily test. So we need to read daily, and also like we had a daily, at least 10 minutes we used to devote for the test. So practicing is a good thing, and you can practice from book back questions. So that will help you reinforce the concepts you learned. And coming to the third thing, do you have problems avoiding distractions? Then make distractions difficult, right? For example, if you're distracted by your phone notifications, one thing you can do is to keep your phone far away or in a place which is difficult to reach. So that would be helpful. And be consistent in your learning. So it shouldn't be like just you're learning 1 week continuously, then you're not in touch at all for 1 month or 2 months, and then you just revise. So that is not going to help. So you have to put in consistent learning. So maybe daily devote some half an hour. Half an hour daily is more than enough. And when you do it for over a long time, 1 month, so it is a good enough effort from your side. And don't compromise your health. So one thing I always suggest is never compromise on your food and sleep. So these are the two most important things that regulate your health. So you may think like one day I will learn until night 2 o'clock, and next day I can take rest. So again, that is not going to help, right? So in the long run, you may fall sick and you may waste like 2 months of your preparation of whatever you're going through, right? So always keep health your priority. The good thing is like you need to have a balance in all the things. Yes. Okay, moving on. So these are the recommended books. So in my college days, I used this Signals and Systems by Alan B. Oppenheim. It's a very good book. And recently I have been hearing this book a lot, Linear Systems and Signals by P.P. Latty. It is also a very good book, and there are lots of book back questions in this which will be helpful for you guys. Okay, so now let's come to the actual topic of what is a signal, right? So here I have put some images which depict a signal. So this is like the fire signal you give when you're lost or you want to be rescued by someone. And this is a picture of Mona Lisa, and you can see all these tiny squares, right? So these are the pixels. So each pixel is conveying the information of the color, right? And if you see here, this is the sound vibrations, sound signals that get travel through the air and reaches our ears, and we are able to sense them. And this is the traffic signal. So it says you whether to stop or go, right? And this is an Indian map showing the temperature gradient across the planar regions, right? So one thing you can observe from all these examples is that they are conveying some information, and it is through some form of physical interaction, right? Or to say physical phenomena, right? So we'll go ahead and define the signal more formally. So signal is a set of data or information which may describe a wide variety of physical phenomena, right? So it is a set of information or data, and it is describing a wide variety of physical phenomena. And the information in the signal is contained in the pattern of variation of some form. Yes? So only there is variation, we get some information about it. Correct? And this is an example of a sinusoid signal. So you can see it has amplitude, and it has what is called as a wavelength, and it also has a frequency, right? So these are all information contained in the simple sinusoid. So you can imagine other signals as well containing many information. And coming to mathematical representation of a signal. So signals are represented as functions of one or more independent variables. So what are independent variables, right? If you go back to our previous example itself, if you see this sound signal, this variation is a function of not time, right? So at time also it is varying. Let's say the disturbance at this point is varying with time also. But if you take a snapshot, it is no more varying with time. But if you see, it is varying as a distance. So here the independent variable is distance. And it is the same here, correct? Here also it is both the axes. So both x and y, the pixels are varying. This is the same case with this. And if you take a traffic light along the time axis, it is varying, right? And like every 60 seconds you have a red light and such and so. And this is a simple RC circuit, right? Which has a voltage and it has a current. So this can also have variation with time. So the independent variable is the one which the signal itself is depending on. Okay, and as we already saw, it needn't always be depending on time. So it can be space. Space, I mean the coordinates and other things, right? Okay. And what is our area of interest here? Because it is an electrical engineering course. So we will be focused on electrical signals. For example, voltage, current, charge on a capacitor, and so on. And we'll generally consider the independent variable as time, but it needn't be the case in few places. So we have to assume any one variable. So we'll, for convenience, assume it as time. But even in electrical engineering, it needn't always be the case, right? Even if you see in image processing, you need to consider other variables like the x coordinates and y coordinates as well. So for convenience only, we are considering it as time, but it needn't be the case always. Okay. Now coming to a system. So when you say system, what comes to your mind, right? So this is the nervous system of a human beings. So it is an interconnection between the brain, spinal cord, and the nerves, right? And if you see here, it is a pulley. It is a simple mechanical system. So it transforms the force from one side to the other. And this is the infotainment system in a car. So it takes the incoming data and displays it for you. And it also interacts. It takes inputs from your side and then processes it. And this, if you see, it is the picture of Chandrayaan-3. It has something called as a propulsion system and various other integrated systems inside it. So basically, a propulsion system helps in propelling the module, right? So these are some examples of systems. Now we'll formally go ahead and define what is a system. So a system in a broad sense is an interconnect of components, devices and subsystems, right? Some interconnection between these three. And it may be viewed as a process in which the input signal is transformed or additional information is extracted. So we have a signal which we call as an input signal. We pass it through a system which is defined to do some function, let's say of transforming a signal or extracting some information from that signal. And it can have an output signal depending on whatever it has done, right? Output signal. So the system is simply like this. This is a system This is an input signal and some output signal we have. And mathematically, how do you represent it? They can be represented as functions acting on input signals to produce output signal. So previously we saw that signal itself is a function of an independent variable. Let's say S of t, right? S is the signal and t is some independent variable. Let's call it time. And what is a system now? System is nothing but a function on this signal itself, right? So that is the mathematical representation. And the function can be realized either using physical components, hardware. For example, whatever we saw previously, right? So this kind of things, propulsion module and everything, or a simple RC circuit. So simple RC circuit is also like a hardware implementation or hardware realization. And it can also be realized using an algorithm, which is a software implementation. Let's say you want to implement finding the average of the incoming signal. So it can be done in the software. So these two types of implementations are possible. And systems are usually described by an ideal model to as closely represent the real scenario as possible. So what it means is, I'll explain it using an example. So if you have a metal ball and you're dropping it from a height h, so you may want to find the velocity at which it reaches the ground. So while doing the calculations in physics, you usually neglect the air resistance. So air resistance is neglected. So that is an approximation to the actual scenario, right? So systems are also can be like usually represented by considering only some important variables which account for the maximum involvement in the given scenario, and other variables can be neglected. So that is what it means. But in another case, if you take a feather, then it may not be the case that you can neglect air resistance. In that case, air resistance is not negligible. So it depends on the engineer's point of view, like the engineering scenario point of view, and the engineer should choose the proper variables accordingly. So moving on, we come to the size of a signal. As human beings, sizing or measurement is most important to us because it helps us understand how much that anything is contained in it, right? So like that size of a signal also matters. So it can matter for many reasons. For example, I can say our interested signal, and there may be some undesired signals also. So when we are transmitting our signals from here to, let's say, in some other place, so these undesired signals also join these interested signals. So then the size matters, right? So our interested signals should be at least sized little more than this undesired signals so that we get a good transmission. So in other way, when we are designing a system for a particular input signal, so we may design the system, choose the system components based on the strength of the input signal, right? Otherwise it may fail. For example, even if you take a simple resistor, it has a particular rating, voltage, current, and power rating, right? So that's why the size of the signal matters. So there are a lot more other reasons as well. We'll see that as we progress in the course. But for now, to define the size of a signal, it is a measure of the strength or largeness of a signal, right? So we have defined that it is the measure of some strength of the signal. And if you take a simple signal, it has what is called as amplitude, and it also extends in time, correct? Okay, so here I have two examples. One is a triangular waveform which has a which is on for a limited time period, and you have a sinusoidal which continues from -infinity to infinity. So it is a very long signal, right? But its amplitude is limited to 1 volt, plus minus 1 volt. On the other hand, this triangle signal has 2 volt. Suppose we want to gauge these two based on some measurement. So what is a good measure to gauge this strength of these signals, right? Or for any signals. This is just an example. So first let's ask, is amplitude a good measure, right? So it is like the triangle is having 2 volt, but the sinusoid is having just 1 volt as a peak. But if you see, the triangular waveform is limited in time, but the sinusoidal waveform is extended long, right? So amplitude alone is not enough. So both amplitude and the longness of the signal matters, right? So both amplitude and time matters. But what about the negative values, right? So even if it is like negative minus 120, it is still a very high signal. So negative is just for us, for our convenience, we have said positive and negative. If you just invert the polarity, then it is going to be plus 120 volt, right? So the negative values also is like, if you have a huge negative value, that also matters. So then what do we do to take all this into account, and what can be almost a good measure for a size of a signal? So then we come to the signal energy. So energy of a signal x of t is defined as the area under the graph x square of t. So if you take any signal x of t, let's say the sinusoid itself, once you square it, so this is x of t. If you square it, all the negative values are going to disappear, correct? So it will be something like this. Now you take the area under this graph. So mathematically, how do you describe it? So let's say Ex is the energy of the signal x of t. Then we have integral x square of t and dt, right? And you have to integrate it from minus infinity to infinity. So now you have solved both the problems of the longness of the signal and the negative values also is taken care, right? So this is when x of t is a real signal. So the definition can also be extended to complex valued signal. So complex valued signal, what do you have? The same like explaining like real numbers and complex numbers. So you can have a of t plus jb of t. So this is the real part and this is the complex part. So now you can't take directly the x square of t and compare, right? Because you can't compare two complex numbers. So if you had gone through basic math course, even in your 11th and 12th standard, you would have come to know the fact that you can't compare two complex numbers. So then how do you define x square of t? So that's where we have the modulus for a complex number. So we can take the modulus square. Then it is nothing but a square of t plus b square of t. Both a and b are real. So now we are able to perform the integration. So minus infinity to infinity mod x of t whole square dt, right? So this is the definition of the signal energy. But there are some signals which extends from minus infinity to infinity. For example, simple signal like sine t. So this itself is like extending from minus infinity to infinity. And x square of t, everything become positive. So then if you do this integration, the value will surely tend to infinity. So then what do you do in that case? Like I see, for example, if you take sine t and sine t 2t. So both these are then tending to infinity. Then you don't have a good measure for these very long signals, right? Extending from minus infinity to infinity. So then what do you do in that case? So then we define signal power. So the same questions I had asked. What about signal that has infinite energy? Do they all have same size? No. So we define the power of the signal as the time average of the signal energy. So what do you do? So you take a particular interval. Let's say minus t by 2 to t by 2. And there is some signal here. Okay. And you find this value. So area under this. So x square of t dt from minus t by 2 to t by 2. And you take the average of that. Right. And what do? You extend this t to infinity. So both sides it will go to infinity, right? So limit t tends to infinity. So this will be a good measure for the signals that are having infinite energies, right? For example, the same case as a sinusoid. So let's say sine t and sine 2t or sine 2 sine t, right? That will be simpler. So in terms of power, what are they differing in? You can just consider both are periodic signals, right? So you can just consider one period. So let's say from here to here, right? Let's say t2 minus t by 2 or anything, t by 2 to minus t by 2. And when you divide it, it is going to have a sinusoidal signal is going to have a particular value, finite value it is. But 2 sine t will have a value that has this whatever is there here, right? So since you are considering x square of t, then it will have a value of 4 into that finite value. So it is equivalent to saying sine of t and 2 sine t. It is like 2 sine t is 4 times much bigger signal than sine of t, right? So that is where the signal power helps. Okay. Moving on. Is signal energy the actual energy? Correct? That's a fair enough question to ask, right? We are calling it energy and we are calling it power. So is it an actual energy? Actually, it is only indicator of the energy capability of the signal. So what it means is, suppose you have a voltage V of t flowing through a resistor R. So then the power is given by V square of t by R, correct? And second example, if we take a capacitor which has of value C and which stores a charge such that the voltage is V of t, then the energy stored in the capacitor is half CV square, correct? So now if you see, as energy or power, what we are saying is this term. I'll highlight in some other color. So this term. So this term, right? This V square term. But if you see, all these other quantities are not coming into picture when we define the signal energy. So that is why we say it is only indicator. It is not the actual energy, but it is we can call it as an energy capability. So if V square of t is large, then we can say the actual power or actual energy is also large. So it in some way signals how large is the power, but it is not the actual value. So then what are their units? So it depends on the quantity x of t involved. So V square of t. So we have defined the energy as, let's say, the voltage, V square of t dt. Then what will be the units? For V square it is volt square and for dt it is seconds. Because you are integrating with respect to time. And if it is current, it will be I square of t dt. So the units will be ampere square seconds. So then what about power? So power is nothing but the time average. Right? So this quantity is going to be same. But you have 1 by t factor. So 1 by t is you will just divide by seconds. So for voltage it is volt square. And for current it is ampere square. So guys, don't be baffled by so much mathematics even in the introductory slide itself, right? So you can slowly pick up the pace, and this is just an introduction. We'll start fresh and I'll describe these concepts once again when we go to the first lecture, right? So keep learning. You will get to the pace of it soon enough. Okay guys, take care. If any comments, please post below. Thank you.